Why, hello there, everybody. What's going on? Welcome back. No, you're not seeing things. This is your math instructor, Daniel Valvo. Even though I said before, I was very excited. I was like, well, I was tired. I was like, oh, math class is over. I made the exclamation. I kind of regret the noise I just made. It was a little different than the one I did in class. It's kind of a bad impression of myself. But the point is, I said math class is over. So what am I doing here? Am I an apparition? Maybe. But I am still real. And I'm still here to teach you math if you want it. Math class, discrete math is over. Everything you technically need, I've already taught in class. I'm just giving you guys a little bit of extra practice problems in case you want it, because we kind of ran out of time today. We're only really able to do one example for all of the one-to-one onto and bijection stuff. So I want to do more examples for you if you want it. So if you want, stick around. If not, leave now. Okay, we got rid of them. Let's start talking about one-to-one onto and bijections and all that stuff. So what I'm going to do is first I'm going to share my screen. Nailed it first thing down. And the next thing I'm going to do is I'm going to go through a bunch of functions, and we're just going to talk about if they're well-defined, one-to-one and onto, and prove them all, or prove them if we can and disprove them if they're not. So we have a lot to do. First up, let's talk about this function right here. F of x equals ln of x. And I immediately regret writing it like this, because I contend the way it's written right now, it's impossible to know whether or not this function is well-defined, one-to-one or onto. Why? I guess you can't answer, so I'll answer because no one's here. The point is we can't tell because nowhere here have I specified the domain or the codomain, right? Remember, we always need, when we define a function, we're not in middle school anymore, when we define a function, we first say what the codomain and the domain is, or domain and codomain is. So I'm going to say this is a function that goes from the domain of 0 to infinity to the codomain of the real numbers, not including 0, by the way. And it does this specifically via the function f of x equals ln of x. That makes me feel much better. So first, let's talk about if this function is well-defined. So really, in this exact problem, we don't have much to do because this function just is ln of x, so it's going to inherit all of its properties from ln of x. But importantly, we should notice that ln of x is perfect for this domain right here. This domain was chosen very, very carefully for ln of x, actually, because this is exactly where ln of x is defined. Remember, you can't define ln of x for negative numbers. Ln of -4, what's that? Makes no sense. Ln of 0 makes no sense as well. So we don't have ln of 0 or ln of negative numbers, but for anything greater than 0, ln of x is defined. So we should first note for all x in 0, infinity, ln of x is defined. And maybe not more importantly, but equally importantly, ln of x has one output for all these x's, right? And the kind of one reason we can see that is because if you remember the graph of ln of x from like calculus and things like that, the graph looks like this, where this is x, this is y, and this is y equals ln of x. And notice it passes the vertical line test. You might have heard of this before. In the vertical line test, like if you graph a relation like we're doing right here, it must pass the vertical line test to be a function, because passing the vertical line test is equivalent to being well-defined. Why is that? Well, it's easier to see an example where it fails the vertical line test. So imagine you had a relation, I should say, it's not a function, that looks like this. Notice this fails the vertical line test. You could draw a vertical line, for example, right here. Let's say this is at x value, x right there. And then let's say this is A and this is B. Well, this red line is the graph of whatever function we're saying fails the vertical line test g of x. And so what this graph is telling you is that, so on the y we graph g of x, on the x we just graph the input, right? So this is telling you that if you input, actually I'm going to use a different letter here for x to avoid confusion. Let's say c. So this is telling you is that if you plug in c to g, you kind of get two y values, a and b. This is saying that g of c kind of equals a, and it equals B, where A and B are certainly not equal to each other. And so what that means is G of C has, or G has two outputs when you plug in C, and that's no good. G relates C to two things, not one thing, meaning it's not well-defined. Well-defined means you want every input to have exactly one output. So that's no good. But if you look at our ln of x, the function we actually care about here, this passes the vertical line test, right? Every vertical line goes through exactly one point. And what that means is there's no point you could find down here. There's no point you can find where this x value gets mapped to two different inputs. It just doesn't happen. So that is what it means, really, for x to be well defined. If it is defined and it passes the vertical, if it's defined on the whole domain, if it passes the vertical line test in the whole domain, that means that f of x has an output, but it doesn't have multiple outputs. Therefore, it's well defined. So note, for all x is 0 infinity, ln of x is defined. Further, it passes the vertical line test. So at no point does it have multiple outputs. Thus, f of x equals ln of x relates each input in 0 infinity to exactly one output in R, meaning f is well defined by definition. There we go. So f is well defined, so we know it actually is a function, not just any old little relation, right? It's special. So the point is, it is well defined. Next, let's move on to proving or disproving that f of x is 1-to-1. So remember that a function being 1-to-1 means that there are no two inputs that map to the same output. And so there are no two inputs that map to the same output. What that really means is for all A and B in our domain, such that A does not equal B, that implies f of A does not equal f of B. So really we do, it's a simplification, saying that for all A and B, actually I'll do this correctly. I should say for all A in 0 infinity, for all B in 0 infinity, A not equal B implies that f is not equal f of B. The point is, any two distinct inputs will map to two distinct outputs. They'll map to two different things, not the same thing. That's the whole point of being undefined. And, or sorry, the whole point of being 1-to-1. If you take the contrapositive of this is saying that for all A in 0 infinity, and for all B in 0 infinity, f of A equals f of B, negate that, implies that A equals B. And we talked in class why this kind of makes sense. It makes sense because if our function truly is well-defined, well, that means that if you have an A and B such that f of A equals f of B, then A and B must be the same thing because we don't want any two different elements to map to the same thing. So, yes. So, do we think our function here is 1-to-1 is the question. Well, let's kind of draw it again. Think about it. It looks like this, remember? And so the question is, does it look like any two inputs will map to the same output? Well, if any two inputs will map to the same output. Not really, right? I mean, this input maps down here, this input maps down here, this one maps here, then it goes up and up and up and up and up and up and up. But the point is, it never kind of comes back on itself. Like a function that's not 1-to-1 looks like or it might look like this, or it might look like this. The point is it'll fail the horizontal line test. It has to, if it's not one-to-one, because it has to have 2 points from different inputs, right? Different x values, but with the same y value. But that's not how our ln function looks. Our ln function looks like for any 2 distinct x values, we'll have distinct y values. So I should have proved that. So claim is that f is 1-to-1. Proof. So we're going to do the proof like the standard way we talked about, which is technically a contrapositive proof right here. And that is we're going to assume there exist A and B in our domain such that f of A equals f of B. And note we're talking about our function is ln, so by substitution, this means that ln of A equals ln of B. But, okay, actually, let's work with this. Let's work with this. So I'll say note. Ln of A equals ln of B. This implies ln of A minus ln of B equals 0 by subtracting ln of B from both sides. Well, this implies here, here's the key part, here's the interesting part. Recall a nice little math fact. A nice little math fact that says that the ln of A divided by B equals the ln of A minus the ln of B. And remember this? This is the whole thing with the ln rules. We also have the A times B would be ln of A plus ln of B. A raised to the B is B times ln of A. A bunch of those. And we're going to take advantage of those right now. Because we know ln of A over B equals ln of A minus ln of B, we can run that backwards. Equal signs go both ways, right? So this means that the ln of A over B must equal 0. However, let's remember, right, what ln means. Ln, well, actually, we can actually, let's do this. Let's do the classic thing of ln's where we raise e raised to that on both sides, right? And this gets us, and I'll say, wait, this is by ln rules. This is by raising e to both sides. And this implies e and the ln cancel out, and we get a over b equals e to the 0, which equals 1. You could think about going from here to here with this step, although I personally don't like this. I prefer to think about what ln of A over B means. Ln of A over B equals 0. Right, the ln of A over B, that means ln of A over B, it asks the question e raised to what equals A over B. So this means that e raised to the 0 must equal A over B. Because remember, ln of A over B, what it equals answers the question e raised to what equals A over B. So it equals 0, we know e to the 0 must equal A over B. But so either way works. But either way, you get that if ln of A over B equals 0, A over B must equal 1. The other way you can look at it is just memorizing the fact that ln is only 0 at 1. We're plugging in 1. The only thing you plug in ln and get 0 is 1. Either way, you end up with A over B must equal 1. And this is by simplification. And then let's go below the glare. I'm getting better at this. There we go. End up with A over B equals 1. And then this eventually implies that A equals B by multiplying both sides by B. So notice we started by assuming there's just an A and B and 0 and infinity, it's just that f of A equals f of B. And we've proven A equals B. So what this means is that if we have, if there are two inputs, or yeah, if f of A equals f of B, so if these two inputs go to the same output, well, they must not be two different inputs at all. They're just the same number here, A equals B. Therefore, f is 1 to 1, otherwise called injective. All right, soak that in. So ln is 1 to 1. That's great. I guess it's great if you want that. I'm kind of, you know what, it is great. I was going to say that I'm kind of neutral towards math, but I'm not that jaded yet. I care. ln's great. I love it. Good for you, ln. Now let's go for onto. So recall a function f is onto if for all y in the domain, or sorry, in the codomain, so for all possible out, so remember, like R tells you where the outputs are going to be. So for every possible element in the set of where the outputs are going to be, there exists an x such that f of x equals y. So this says that everything in R here gets hit. Everything in the codomain gets hit. For anything in the codomain, there exists something in the domain, so that f of that equals that thing in the codomain. I think that makes sense. Whereas finding, yeah. So, I mean, let's just prove it. So the proof goes like this. Oh, by the way, I'm sorry. We should first ask ourselves, is ln of x 1 to 1 or onto? And again, I'm going to go to the graph because it's kind of the best visualization we have for ln of x. And if you look at the graph, well, we know kind of this should go down to negative infinity here. So every value between 0 and negative infinity gets hit right here. We also know that f, from calculus, know that f is an ever-increasing graph. Like this is not an asymptote. This increases forever. It goes to infinity slowly, but it goes to infinity. So this should eventually hit everything. This should eventually hit all y values from 0 to infinity in the positive direction. So this should be onto. It should hit all the real numbers. So now let's prove it. All right, proof. Our proof goes like this. So we want to prove a for all statement here. So we're going to say is let y be any arbitrary / particular element of the domain, sorry, of the codomain, which here is R. And now we want to show for all y and R, we want to show there is some x such that f of x equals y. Let's look at this right here, right? So f of x equals ln of x, right? So what we're trying to show is that for any y, there's some x's that y equals the ln of x. So what does this x have to be? Like, what's x have to be so that we can plug it in ln and get y? That's the question. Let's just solve for x, right? We can solve for x by doing e to the y, e to the both sides like this, and we get that e to the y must equal x. And we can check this. We can check, and we see that, hey, ln of x equals e to the y does in fact equal y. So this means that there is a number, well, as long as x, as long as this is in domain, as long as it's in our domain, then we've just found an element x in our domain, so you can plug into f to get y. And y was arbitrary, meaning we could do this for anyone. So the only thing we have to prove is that e to the y is actually between 0 and infinity. That's actually going to be a cinch. So I'll say consider x. I'll say let. We're doing more than considering. We're going to straight up let x equal e to the y. Note, since the exponential e to the y is positive for all inputs, e to the y is going to be in 0 infinity. This is our positive, set of positive numbers for any y. Or maybe I'll put it like this. Notice since the exponential function, the exponential function being e raised to something, is positive for all inputs, e to the y must be in here. So y is this particular element of the codomain, and we note that the exponential function is always going to be positive, because if you look at the exponential function, right, it looks like this. It's always positive. Since the exponential function is always positive for all inputs, it doesn't matter what y is. For this arbitrary y, e to the y is still going to be positive. Yeah, the point is e raised anything is positive, so e to the y is positive. That's all I should say. Anyway, so e to the y is in 0 infinity, which is the domain. Further, f of x, which equals ln of x, which equals ln of e to the y, is going to equal 1. Therefore, there does exist an x in 0 infinity such that f of x equals y. Hence, the claim is true, f is onto. Yeah, and there we go right there. This proves f, beyond any doubt, that f is onto. For anything you pick in the codomain, I can find you an element in the domain, mainly e raised to the element of the codomain you picked. I can find an element in the domain that you can plug into f to get that element in the codomain that you picked. Yeah. So that's that. And I guess one last thing I'll say before we end here is I'll say, note, since f is a 1-to-1 and onto function, f is well defined. I'm sorry, we already know it's well defined. It's a good function. F is a bijection. We call functions that are 1-to-1 and onto bijections, or injective and surjective, by the way, we could have called this. Yeah, so there we go. That is ln of x for you. It is well defined onto 1-to-1, making it an injective and surjective function, making it a bijection. Any questions? Email me if so. Okie dokie. What's next? Next we have, I'm gonna call this out so it doesn't matter. Next we have, ooh, this one's freaky. Yeah, let's do that. Let's go ahead and, okay, hello, we're back. Let's go ahead and do an example. The example being let f of x, it's not different this time, just for fun's sake. Let g of x equal x squared. Once again, I have to define the domain and codomain. I'm so sorry. Let's go from R to R such that by g of x equal to x squared plus the absolute value of x. Okay, I don't know why you so much trying to write that, but I hope you plan to write that and mull this over. So this is our function now. So again, we're going to try to decide it's well-defined, one-to-one, or onto, or and or, you know what I'm saying. So let's do well-defined first. So is this function going to be well-defined? Well, remember, well-defined means that for any possible input, there's exactly one output, meaning it's defined everywhere, but it does not have multiple outputs. And the good thing about this is functions will inherit the properties of their kind of sub-functions here. So here we have an x squared added to an absolute value of x. And so let's note that the function, note that x squared has one output for each input in R, and so does the absolute value of x. For every input, both x squared and absolute value of x just give us exactly one output. Let's say exactly one output here. Thus, because addition also gives a single output for each of its possible inputs. G of x, which equals x squared plus x, gives exactly one output for each input in R. Thus, G is well defined. So here's what we're trying to get at here. What's happening is x squared for each possible input, imagine an input, like 1, 2, imagine one. Those are good inputs. E, whatever, because we're all of R. Imagine any input in R. X squared is going to have one output. And the absolute value of x is going to have one output. And when you add one output to one output, addition just has one output, right? Like 5 plus 4 is not 9 or 12. It's always 9, right? And so since x squared, x, and this plus here all give one output for every input, that means this whole function combined will just give one output for every input. It's impossible not to. Therefore, G is well defined. Oh, I switched my well defined. There we go. Just like that. So now let's work on to one-to-one again. So do we think this function will be one-to-one? Not likely. Yeah, not looking likely. If you look at it, g of x equals x squared plus the absolute value of x. Why is that important? That's important because notice that g of 1 will equal 1 squared plus 1. Oh, I'm sorry. Wait a minute. This is why I'm confused. I don't want to go from R to R here. I want my domain to be just 0 to infinity again. This time including 0. There we go. Thank you. I was thinking in my head this should be a one-to-one example. Where did I go wrong? Yes. So this function right here goes from 0 to infinity to r. That's important because notice x squared, right, definitely has a multiple inputs that go to the same output, right? Because negative number squared is the same thing as positive number squared. And similar, I think, with absolute value of x. So for example, g of -1, if it was defined there, would equal -1 squared plus absolute value of 1, or -1. -1 squared is 1, absolute value -1 is 1, this would be 2. And g of 1 would be 1 squared plus 1, which should also be 2. So if we included the negative numbers here, if this is all of r, then we could find two inputs, -1 and 1, that went to the same output. Therefore, by definition, this would not be well defined. But luckily, I caught my mistake, and we're not dealing with r as our domain, we're dealing with 0 to infinity as our domain. And I believe this will actually be 1-to-1. Why do I think that? Well, I think that because imagine, or really, x squared is an increasing function. The bigger x you plug in, the bigger x squared you get. Absolute value of x on 0 to infinity is a, I wouldn't even need that. Well, we'll keep it anyway, just for fun. The absolute value of x on 0 to infinity is, again, an increasing function. The bigger x you plug in, the bigger absolute value of x you're going to get out. So the point is, it seems to me that if a does not equal b, if you have two distinct inputs, like if a is less than b, then g of a should be less than g of b. So they shouldn't be equal. It should just keep increasing. So they'll never be equal. But how do we prove it? That's a good question. And so the way we prove it is, let's go by the following. Wait 1 second. Yes. So the way we prove it goes by the following. Let's go ahead and say 1-to-1. One-to-one claim G is 1-to-1 proof. So the proof that something's 1-to-1 always goes the same way. You assume that there's elements in the domain A and B, so that G of A equals G of B, and then prove if that's the case, A must equal B. And once you've proven that, you've proven there can't be two distinct elements that go, there can't be two distinct elements in the domain that map to the same element in the codomain, because you just showed that if any two elements map to the same element, they have to be the same. So, proof, assume that G of A, assume there exists A and B in the domain 0 to infinity, including 0, such that G of A equals G of B. All right, then what happens here? Note by substitution. So for the definition of G, this means that A squared plus A is going to equal B squared plus B. Yes. A squared plus A is going to equal B squared plus B. All right. Now let's do some calculations. Or I'll just say by substitution here. So I can use the word note and not feel bad when I start essentially the same thing twice because the 5th grade teacher told me not to. So let's say note A squared plus A equals B squared plus B. We want to eventually get around to showing that A must equal B. That's the whole idea. We want to show A's got to equal B. So what I'm going to do is I'm going to try to factor some things here. I think that'd be a good idea. So I'm going to say, let's subtract both sides by B squared and B. By subtracting B squared and B from both sides. So the b squared and b go away here. We get a 0. We're going to subtract minus b squared here and minus b here. But notice we can factor this a minus b, a squared minus b squared, right? Because a squared minus b squared equals a minus b times a plus b. And that just stays the same. And this is by factoring. There we go. And then we can factor, we have an a minus b here and a minus b here, so we can factor again. Also by factoring. And then, thus, a minus b equals 0, or a plus b plus 1 equals 0 by the zero product property. The zero product property, or you can put it, but I like to name it. It's the zero product property is a thing that says that if two things multiply to equal 0, one of them's got to be 0. So now a minus b equals 0 or a plus b plus 1 equals 0. Notice we want this to happen. Because if a minus b equals 0, add a b to both sides, a equals b, proof done. But what about this guy? We have to prove this doesn't happen. If this can't happen by elimination, this must happen. So why can't this happen? Why can't a plus b plus 1 equal 0? It's all because of the domain. Remember, a and b come from the domain 0 to infinity, meaning they're non-negative numbers. So 1 plus a non-negative number has to be greater than or equal to 1. The smallest it can be is 1. You can't go less than 1 because you're just adding a non-negative number. And then that added to another non-negative number, again, has to be greater than or equal to 1. It cannot go down, cannot be less than 1. So this sum has to be greater than or equal to 1. But if it's greater than or equal to 1, it certainly cannot equal 0. So that's what we're going to prove. Note, since a and b are in the set 0 to infinity, we have that. Oh, yeah, by the way, I forgot to mention that this absolute value, it meant something before when there was an R here, but it means something now because for when you're in positive real numbers, the absolute value of x always just equals x. So we're totally fine. Anyway, though, so that's a minus b equals 0, a plus b equals 0. Back down to here. That's why I got rid of the absolute values here and here, because this doesn't matter on our domain of the of non-negative numbers here. So let's just pretend like it was x from the beginning because it doesn't matter for our fixed domain. Anyway, note since a and b is in 0 to infinity, a must be greater than or equal to 0 and b greater than or equal to 0. Hence, a plus b is greater than or equal to 0 plus 0, which just equals 0. So a plus b is definitely greater than or equal to 0. And then if we come down a little further, and literally I'm going to write further, a plus b plus 1, which is greater than or equal to 0 plus 1, which equals 1, by adding 1 to both sides. Then since a plus b plus 1 is greater than or equal to 1, a plus b plus 1 certainly cannot equal 0. Therefore, by elimination, a minus b must equal 0, which implies a equals b. So g is 1. So g is 1 to 1 as desired. Good. Good. So yeah. This is how you prove that G is 1 to 1. Again, you just assume there's just elements A and B in the domain. So the G of A equals G of B, and then show A must equal B. That means there's no two distinct elements that map to the same element. Therefore, it's 1 to 1. All right. Now let's do onto again. So onto, what color did I use last time? Was it green? No, it was pink. Use pink again. Now let's prove onto, or disprove onto. Let's see here. Well, will it be onto? What do you guys think? I don't think so. I don't think so. Onto means that for all y in our domain, which is R here, there should exist an x in our codomain, which is 0 infinity, such that y equals f g of x, which in this case equals x squared plus x. So we think for any real number, we can plug something into our function here to get that number. What about like -5? Whoops, right? -5 is a classic counterexample to this because for any 0 to infinity, for any positive number or non-negative number, x squared is going to be non-negative, x is going to be non-negative, so x squared plus x is going to be non-negative. You can't add two non-negative numbers to get a positive number, at least not in my world. So what that means is that g of x is going to be at least non-negative, probably positive. So it's not going to hit any negative numbers, even though there's a crap load of negative numbers in our codomain. So the range will not equal the codomain. The range will in fact be all the non-negative numbers. So we're missing a bunch. So it's not onto. And so the way you disprove onto is you simply have to disprove this claim, or really prove the negation of this claim. The negation of this claim being there exists a y in R such that for all x at 0 infinity, y does not equal g of x equals x squared plus x. All right, that's how you negate things. Flip the quantifiers, negate the predicate, and we're good. And that's going to be more true because like -5 is a good example. So let's prove that G is not onto, not surjective. Proof. Let's consider y equal -5. Note -5 is in R. This is just verifying that y is actually in our domain here. Next, or then, or yeah. Next, note that, or next, how should I put this? I guess we kind of have to prove this by contradiction. Because it all comes down to the fact that this is going to be positive, and so it can't equal -5. But the way we actually need to prove that rigorously is like assume it does work and then show it can't work. Or yeah, you know what I'm saying. So assume for contradiction that there is an x in the domain of 0 infinity such that g of x equals -5. So the whole thing we're doing here is I have y was -5, and now I want to show that for all x in the domain, y will not equal g of x. That's how we know it's onto. There's nothing you can plug in to get -5. But to prove that you can't do that, we kind of need contradiction. And contradiction is going to assume that there is some value for which you can do it. That will prove that's ridiculous. So therefore, for all values you can't do it, that covers this, and we're done. So assume for contradiction, there's an x in 0, 5, or 0 infinity, just the g of x equals -5. Note or I should say by definition of G, we have that x squared plus x equals -5. Note, since x is in 0 to infinity, x is greater than or equal to 0. Because x is greater than or equal to 0, x squared, which equals x times x, is a product of numbers greater than or equal to 0. So x squared is greater than or equal to 0. So we have x greater than 0 and x squared greater than 0. Since x greater than 0 and x squared greater than 0, g of x, where g equals x squared plus x, is greater than 0 plus 0, which equals 0. Right? If you have a sum of two things, each of which greater than or equal to, this is greater than or equal to 0, this is greater than or equal to 0, so the sum works out. So g of x is to be non-negative, as we're getting at. G of x is to be greater than or equal to 0. And this is a contradiction. Or, lastly, I should say, because -5 equals g of x, we have -5 greater than or equal to 0. Here's our contradiction. -5 is not greater than or equal to 0. Thus, assumption is false. And our assumption was there's something that you could plug in, that there exists an x you could plug in to get -5. So that assumption is false. That means for all x you plug in, you won't get -5. Thus, for all x in 0 infinity, g of x does not equal -5. Hence, the claim is true. I'll block it. The claim is true. G is not onto. Or maybe I'll just say G is not onto. There we go. So you prove that G is not onto by proving the negation of what it means to be onto. So proving something's not onto, you show that there must exist some value in the codomain that cannot be reached by G. No matter what you plug in, you can't get it. It's a hard to reach spot. Okay, so I guess tying this all together, because G is well defined, it's a function, and it's onto, but it's not one-to-one, so G is not a bijection. Okay. I think those are the two hardest ones. What's up next? We have, that's a good one. Up next we have, let's define, I'll call it something else. Oh, we're back to this. Kumbaya.